All right, so here's another example of a problem that involves both constant acceleration particle motion and unbalanced forces. I'm going to work problem 54 from chapter 5. So let's read the question and write down givens. Riders on the Tower of Doom, an amusement park ride, experience 2 seconds of free fall, after which they are slowed to a stop in half a second. What is the 65 kilogram rider's apparent weight as the ride is coming to rest? By what factor does this exceed her actual weight? All right, so we've got 2 different time intervals. We've got time interval 1, which is 2 seconds, and we've got time interval 2, which is half a second. What is the 65 kilogram rider? So the mass of the rider is 65 kilograms. That means we know her weight. We know the force of gravity of the Earth on the rider. That's her mass times the gravitational force constant. What is her apparent weight? Okay, so apparent weight is the code word that your book uses for normal force. That's the normal force of the chair on her, or in an elevator, it would be the normal force of the floor on you as you are either speeding up or coming to a stop. And when it's different from your weight, the normal force can be called the apparent weight. By what factor does this exceed her actual weight? Her actual weight is the force of Earth on her. So we do know that. Okay. So we have these 2 time intervals. It seems like we're worried about the part where she's coming to rest. So the rider is going to start out in free fall. That means they're accelerating down. I'm going to draw a motion diagram. And then once they start stopping, they're going to slow down quickly. So let's see if we can draw this. I've got my motion diagram. This is the free fall part in the beginning, and then somewhere around here they start slowing down. And I really didn't do a good job making the times the same because she's slowing down a lot faster than she sped up. So we need to make sure this is happening pretty fast. Okay. So this is the time interval we're interested in. Okay, so what have I done? I've read the question carefully. I've drawn a sketch, label my X direction on the sketch. So I am going to pick the direction she's moving as the positive X direction. Underline all values given to you in the text, associate each with this variable label. I think I've done that. So every number in the variable has a known here. So we have all these. Time 2 is the time we're interested in. That's this time later. Okay. Decide what variable we're solving for. We're solving for a normal force. We need to know what the normal force is. That means we need a free body diagram. Okay. So this is a free body diagram for the rider. The rider is got the force of Earth acting on them, and the rider has a normal force acting up. How do I know the rider has the normal force acting up on her from the seat? So you can see from her motion diagram that she is accelerating backwards. We know that this is a walk like Egyptian kind of situation. That means the unbalanced force must be up. Okay, so we know that. All right, so we want to solve for the normal force. Let's write a Newton's second law equation. That's the apparent weight. And so I picked down as my positive X direction. Let's be really clear about that. That means that the force of gravity from the Earth on the rider is positive, And the normal force from the seat on the rider is negative, and that equals the mass of the rider times the acceleration of the rider. And I can solve for the normal force by rearranging. So if I do that, I'm going to keep the normal force on the left. I'm going to subtract the gravitational force onto the right. And then I'm going to flip all the signs just to make the normal force positive. Okay, so what do I know? I know the weight of the rider. Whoops, I don't want that color. Let's do this. I know the weight of the Earth on the rider, and I know her mass. Unfortunately, I don't know her acceleration, so that's a problem. I really need this. Okay. Oops. So, how do I find that? So I know how long it takes. This is the kinematics part. I know how long it takes her to slow down. If I worked at it, I could probably find her initial speed. And I'd have to get that from the first time interval. Okay, so if I know these two things, then I could use the second kinematics equation, because I know she does stop at the end of time interval 2. So I know this too. So that suggests that I want to use this particular equation, but I do need to know her starting speed. So her starting speed at the beginning of time interval 2 is her final speed at the end of time interval 1. And what do we know about time interval 1? I guess I'm not going to assess this yet. I need some more room. We're not ready for this yet. Let's get rid of that. We're still solving. Okay. So we know she starts from rest and falls for 2 seconds. So we can use the same equation here. Her final velocity equals at plus v naught, except here this is time interval 1. So how fast is she going at the end of 2 seconds of free fall acceleration, which is 9.81 meters per second squared. So that's going to be, and I should have brought my calculator, it's a little less than 20 meters per second. So let's see, I need a calculator. Times 9.81. 19.6 meters per second. Okay, so we're going to plug this in here. So her final velocity at the end of the second time interval is 0. We don't know her acceleration. We do know it's half a second of time. And we know her starting speed is 19.6 meters per second. So the acceleration is minus 19.6 meters per second divided by 0.5 seconds. So 19.6 divided by 0.5. So her acceleration is minus 39.2 meters per second squared. And it's negative, that's good, it's in the other direction. Okay, so now we can go back and solve for the normal force. Okay, so we're going to plug this back in. We have our equation from before. I'm going to put a big box around it. We're going to copy that down to before. So the normal force from the seat on the rider is equal to her weight minus her mass times her acceleration. So her weight is mg minus mr times minus 39.2 meters per second squared. Okay, I can factor out the MR. It's going to be positive 9.8 meters per second squared plus 39.2 meters per second squared. So 9.8 plus 39.2 adds up to 49. It's basically 49.0 meters per second squared. And her mass is 65 kilograms. So all of this times 65 kilograms gives me 3,190 newtons of force upward. Okay, so it's positive, that's good, because it has to slow her down and she's moving down. That works. The units are right. They're newtons because a kilogram times a meter per second squared is a newton. It is larger than her weight. What was her weight again? Her weight is about 650 newtons. Okay, so does that make sense? I think that makes sense. Have we answered the question? What is the writer's apparent weight? So her apparent weight is 3,190 newtons. This is roughly 5 times. Let's see, what factor is this? So what times her weight equals the normal force we can solve. So the factor is the normal force divided by her weight. And we can do that divided by 65 times, where's the times? 9.8. So that's a factor of 5. Does that make sense? Well, it takes her 1/4 the length of time to stop. So it kind of makes sense that the normal force would be 5 times as big, because one of those pieces has to counteract her weight and the other 4 have to stop her. Okay, so we're done.